Hello everyone, my name is WenTao Zhang, and today we will be focusing on Chapter 2, Section 4, Rates and Change and Tangent Lines, right? We will be talking about the following topics. They are average rate of change, tangent to a curve, and the slope of a curve, right? So let's start with average rate of change. This is where your algebra knowledge really kicks in and ties in with calculus, right? Now, I'm not going to explain average rate of change because if you don't know slope, then you should not be in calculus, right? Okay, so let's do an example because, once again, we really don't need to be spending time on this, right? So example number 1, as you might guess from the textbook, right? So the question asks us to find the average rate of change of f of x, right? Which equals x cubed minus 3 over the interval 1 to 3, okay? Now since f of 1, right, equals 0, right? So you have 1 cubed minus 1, that's 0. And since you have f to the, or when you have x equals 3, this becomes 27 minus 3, and this becomes 24, right? And once again, you're going to do change in y divided by change in x. So you're going to have change in y, right? So you have this over your change in x. You have 24 minus 0 divided by 2. And this is 12, right? That's your average rate of change over the interval, right? Or as you Algebra 1 people might like, this is basically your slope, if you haven't figured out already, right? So this is actually one of the, or not one of the, this is probably the easiest math question you're going to do all year. So let's actually level things up and do a slightly more challenging example, right? So the next example, example number 3, asks us to find the slope of the parabola y equals x squared, right here. And we need to find the slope at the point 2, 4, right? So 2, 4, that's right around there, okay? And we have to write an equation for the tangent to the parabola at this point. So let's begin with a secant line through 2, 4 and a nearby point. So 2, 4 is right here, right? And let's pick a nearby point, Q, right? So P is 2, 4, and we're going to pick a nearby point right here, right? And what we're going to do is this nearby point is h units away, right? And what we have here is a delta h, which equals x, or a delta x, which equals h, right? Because you're doing 2 and a value slightly over it. And this is just to exaggerate the delta h, right? Imagine you're looking through this, you're looking at this through like an electron microscope or something, right? And we have, now since our new x value is 2 plus h, we have to also change our y, right? So now the equation is y equals x squared. So when our x equals this value right here, our y is 2 plus h, all of that squared, right? That's not too hard. So next we're going to draw a secant line, or now we're going to draw a secant line through P and Q, and we have that right here, right? And the slope of the secant line is basically the change in y over the change in x, right? So what's the change in y? Well, all right, let's see. We have, so now our new y value is 2 plus h squared, right? That's our new y value at Q. And we have to subtract the original y value, which is at 4, which is 4, right? So you have 2 plus h squared minus 4, right? All of that over h, right? Because now you're doing 2 plus h minus 2. Once again, that's h. So if you factor everything out and you subtract the 4s, you end up with, I think, like h squared plus 4h, and you divide that over h, and you get h plus 4, right? That's the slope of your secant line, right? So we then write the equation of the slope of the secant line and find the limiting value as the slope of the slope as q approaches p along the curve, right? So the secant slope is h plus 4, right? And so the limit of the secant slope as q approaches p along the curve, right? This is limit as q approaches p of the secant slope, right? I'm not gonna write this all out. Equals the limit as h approaches 0, right? H is some infinitesimal value of h plus 4, and this ultimately equals 4, right? You just plug the 0 in since this isn't undefined or anything, right? And so thus the slope of the parabola at P, or coordinate 2, 4, is equal to 4, right? So the m equals 4. So now we have to write the tangent of the slope, tangent to the parabola at P. Now we have to formulate like a linear, like a y equals mx plus b line function, right? So what we have is we have y minus 4, right, equals 4 times x minus 2. This is your y minus 1, y1 equals m times x minus x1 formula, right? And you basically shift this over, add a 4, or excuse me, so yeah, so what you do is 4x minus 8 plus 4, and you get 4x minus 4. This is the equation of your line. So y equals 4x minus 4, right? Now, I need to show you the definition of slope of a curve at y equals f of x at the point P, at the point A, f of A, right? And the slope of the curve is basically calculated, right? So you have m, slope, equals the limit as h approaches 0 of f of A plus h, right? This is your new value, minus f of A, this is your original value, right? And you have to subtract by your delta x, right, basically. So let's move on and do an example that you might find familiar because we did it before in the first video. Alright, so now we're going to do, so now as you might recall, we did a video, or we did the question, was like the rock dropping off this, off the cliffside, right, in the first video. And the function, y equals, so the function y equals 16t squared, gave the distance fallen by the rock, and that was the rock's position function, right? So, I know most of you might not have had physics yet, but there are 3 types of graphs, right? So first you have the position graph. This is like the most boring graph. This shows you exactly where something is at any given time. Then you have the speed or velocity graph, right? And this shows you the rate of change, right? So how fast something is changing at that particular moment. And next, you have the acceleration graph. And I know I'm not supposed to be going into this right now, but you will find you will find this later in calculus. And the acceleration basically tells you how fast you're changing per change, right? So that's so the unit for acceleration is usually meters per second, and you're going to understand most of that later on. But anyways, going back to here, you have so y equals 16t squared is the position function for the rock, right? Now the body's average speed along the coordinate axis, therefore, for the given period of time is the average rate of change of its position function, right? So in order to find its rate of change, you have to take 2 points from the position function, right? And you need to do exactly what we did before, right? You need to be able to find the slope of a curve at a point, right? And this is called your instantaneous speed or your instantaneous rate of change, right? And once again, it is given by this is your instantaneous rate of change, right? You have h approaches as limit as h approaches 0 of f of t plus h f of minus f of t, right, over h. And you might be wondering what the difference is between instantaneous rate of change and slope, and as far as I can tell, it's just you have an a here and you have a t here, right? There's not much difference, right? So once again, we revisit the falling rock, right? Because we love falling rocks. We're physicists. And we find the speed of the falling rock we're asked to find the speed of the falling rock at t equals 1, right? So the position function of the rock is given by, once again, this function right here, right? The average speed of the rock over the interval t equals 1, right? And t equals 1 plus h, right? Is given by the slope, which we saw just now, right? So slope, or instantaneous rate of change, equals f of 1 plus h minus f of 1 over h, right? And so your f, of course, is 16 times 1 plus h squared minus 16 times 1 squared, all of that over h, right? And you're going to simplify, do all that, and you're going to end up with 16 times the sum of h plus 2, right? So the rock's speed at the instant t equals 1, right? So now you evaluate. Limit as h approaches 0 of 16 h plus 2 is 32 feet per second. Okay? That's it.